General Physics 1. And now, here's your professor, Veranga Pereira.
Hello everyone, welcome back. So today we're switching topics a little bit. We're talking about torque, which is kind of the rotational equivalent of a force. Looking at this picture here, I'm showing a skeleton just to get you thinking about where you might encounter the concept of torque. You may not be thinking about it every day, but it's something you actually apply, right? And this is somewhat like a force, but a force applied over some distance about a point of rotation, right? So think about lifting a cup, right? The point of rotation would be your elbow. Your force is coming from your hand, lifting your cup up, and there's a certain distance between your elbow and where you're actually applying the force onto the cup, right? So when the concept of torque, you're kind of combining the idea of a force with some idea of distance. There's some distance involved, which we'll talk about. Once we understand torque, we can start talking about equilibrium, static equilibrium, that involves not just the accelerations being zero, right? So in the case of hanging a light fixture from your ceiling, we talked about, okay, you want the acceleration to be zero, where the net forces are zero at the same time. But it gets a little bit more complicated when you have an object of size, kind of the body, for instance, that isn't a point, right? It has some physical size. Then you also want the net torque, right, the rotational equivalent force, to be zero as well, because if it isn't, there's another form of acceleration. The acceleration's angular acceleration, so you'll rotate in an angular sense, right? So angular acceleration will be there as long as there is a net torque, right? So this is an extension of Newton's laws. We have talked about Newton's laws in terms of linear motion, right? Pushing a box across the floor, that sort of thing. But now we're extending into rotational motion, right? Okay, before we do that, let's take a look at midterm one, the results, right? So here are what the results, the distribution looks like. Overall, pretty good, I think. So if you're towards the right side of this plot, then keep doing what you're doing, right? So don't change much. Keep working hard on the class material, right? Keep doing your homework. Keep asking us questions during drop-in hours. If you didn't do as well as you hoped, we all want you to succeed. We want you to be on the right side of this, right? If everybody gets 100%, that's great, right? So if everybody gets an A, right, everybody's learning, that's the goal. So we want you to be on the right side of this, right? So if you didn't do as well as you hoped, come talk to us, right? So we are happy to go over the exam with you, right? So if you have, this is the nice thing about keeping your scratch work from the exam. If you have your scratch work, we can literally look at what you did for every single problem, right? And just kind of walk through each problem with you, right? So during drop-in hours, you're welcome to contact your TA, the LAs. We set up an individual meeting, right? If you can't make it to a particular time, ideally you can find some time during the drop-in hours. We're available throughout the week, right? But if you really can't find a time, you can send an email, try to find a separate time to chat on Zoom, right? So you'll see your scores, you'll see what you entered into Quest, you'll see the solutions, all of that at the end of class, right? So at 10:30 today, you're gonna see that first on Quest, right? So it will appear on Canvas eventually, but within a day or two. But first, look on Quest. That's where you'll see your score. That's where you'll see the solutions, just like the homework, right? So you can click on the PDF with solutions, just like you can do with the homework after it's due, right? Okay, I think Jericho has got a thread going for this class. So if you have questions about midterm one, anything that wasn't resolved yesterday, or any thoughts, comments, throw it in there. He and Kyla will look at it and let me know what you're saying. So let's take a minute, just if you have thoughts, questions on midterm one, let us know how it went for you. go through the comments after class. It's hard to do it on the fly during class, but they'll give me a kind of a summary, and then I'll go through all the comments. So if we don't get to your particular comment, I'll try to address it after class too. So what's anything popping up so far? Everybody had a good time, everybody. And so what do you all think? It went okay?
There's only like one question that was confusing. It was like the two blocks of the pulley system.
Okay.
Do you know like the steps to solve it?
Yeah, so the one with the two blocks, and so we did a problem in class like that, right? Let me try to find that one. And so it's similar to the one we did. It's a little bit different because I think the one we did was at an angle, right? There was an incline there. Yeah, so this one, switching over to the notes here, kind of like this, right? So it's a similar setup to this, right? So take a look at the solutions if the one on the exam, if it wasn't clear, take a look at the solution, see if that makes sense once you have it. It should be the same procedure, right? So draw free body diagrams, right? Apply F equals ma. That's kind of what you're supposed to be doing on these problems. So hopefully that kind of made sense. Other things in that discussion? Okay, no responses. Okay. If you have questions or comments on midterm 1, throw it in there during class while we chat about other things too, and I will follow up with you after the class. But again, if you're just joining, the results of the exam, for your scores particularly, at 10:30, go on Quest. You should see your scores. You should see what you entered right into Quest, and also the solutions. All of that will be there. Go over it, right? So make sure, particularly if you missed a question, don't skip it saying, okay, too bad, moving on. Don't do that because physics builds on itself, right? So a lot of these ideas that we are working on, they just build up and build up and build up. So if there's some misunderstanding somewhere, even if it's one problem that you missed, make sure you spend some time trying to understand how to solve it. And if it's confusing, come talk to us during drop-in hours. We're available today. Tomorrow's a holiday, but back on Friday, right? Okay, switching to the computer here, what we're talking about today is torque. We're going to talk about torque today, and the concept of torque requires a mathematical idea called a cross product, okay? And so it involves vectors, and doing something with vectors, you can kind of roughly think of it as doing multiplication with vectors. Yeah, multiplication is a little bit more complicated when it comes to vectors, but it's a kind of multiplication, right? So we're learning a new kind of math, right? Arithmetic, algebra, but when it comes to vectors, it's a little bit different, right? So we're learning how to add, how to multiply essentially vectors, right? After that, once we know what torque is, we'll talk about Newton's second law for rotation. You know kind of the regular standard form of it already, but we will now talk about rotation, how it applies. Then we'll talk about static equilibrium, right? Conditions for static equilibrium. Static equilibrium means acceleration is 0, right? So it doesn't necessarily mean something's not moving. It means it's not accelerating, technically speaking. And then we'll end class with talking about the center of mass, right? Because a while back we talked about how, for instance, the Earth and the Moon, they tug on each other as if the force is centered on their center, right? So right in the middle is where the force acts, seems to act, and so gravity, why does that do that? It has to do with kind of the idea of center of mass, okay? All right. So to get us thinking about torque, let's take a look at this demo video. After that, we'll get into a little bit of the math of how to define torque. In this demo, let's take a look at torque. It's a little tricky concept because the direction of torque in particular is perhaps something that you don't think about, or maybe it's a bit unexpected. So the way you calculate torque is that you think about where are you trying to rotate about. So if you have a torque wrench like this, you put it on a bolt, and then let's say you're trying to push this way. So the wrench is rotating about this point, and what we'll do is start off with a vector, r. You'll draw a vector from this point to the point where you're applying the force. So r will be from here to there. Once you have your r, you'll look at the direction of the force. So let's say I'm pushing up like that way. So you'll use your right hand, you'll go r cross F, right? And then you'll get your thumb to point towards me. So that's going to be the direction of torque. So let's put this torque wrench on a bolt, and when we do that, and I try to rotate this, what I'm trying to do is push that way. The force is that way. Like I said, the R from the point here of rotation to where the force is, that's your vector R. So R cross F. So you start off with R, cross with F. Your thumb points towards me, so that's the direction of torque. So when you torque something like a bolt, that's the direction that you're considering. So if you forget, if you've ever tightened a bolt like this, then you can think about which direction do you have to push to get the bolt to tighten. So in this case, if you're trying to tighten the bolt, then I would put the torque wrench right there and push this way, and then the torque acts towards me. So if you forget, think about tightening a bolt, and then towards that direction is the direction torque that you're applying. It'll be the opposite if you were trying to loosen the bolt, right? So if you want to go the opposite direction, the force would be that way. So if you're using your right hand, you go R cross F, and now the torque points towards you. So then you can think of taking off a bolt, right? So then you'd want the bolt to come towards you, and then that's the same direction as torque. So that's a demonstration of torque. All right, so let's go to our notes and define torque. Okay, and a good place to start is a wrench, okay? Because that's probably the most practical thing you've used. If you put together your furniture or something like that, you've likely used some form of wrench, right? And that's a good place to start to think about what torque is. So let's say you have a bolt and you put your wrench bad diagram of a wrench. You'll get the idea. You have a wrench, and let's say you are pushing this way, right? You apply a force that way. Okay? And the other thing to notice is, unlike before where you just had to worry about where the force is, now you have to think about where are you applying the force. So we want to draw a vector, R, from the point of rotation, right? So the bolt is right here, that's where it's going to rotate, and from that point to where the force is. So I'm drawing it a little bit off the axis of the wrench just so that it doesn't clutter up the diagram, but really if you draw a big wrench, you can put it right through the middle, right? From the center of the point of rotation, go find where the force is, right? And that's the direction of R, okay? So that's important. And I talked about in the demo where once you do this, the direction of torque is not obvious. It's not up, it's not to the left, right? It's into the page. Okay, and the way I'm going to draw that is to say this. So we're going to put an X, and this is still a vector, but because I can't draw into the page, I can draw a vector to my right and downward, but it's really hard to draw a vector going right into the page. And so imagine a vector going into the page, and what the X means is kind of like the back of an arrow, right? So you're watching the back of an arrow, and that's what the X is meaning, that it's into the page, right? So this is the direction of torque, Greek symbol tau, still a vector, right? And this is going to depict into the page. Okay, and as a side note, I'll say, as a side note, out of the page is depicted like this, right? So why that? Well, it's like the pointy part of an arrow, right? So if you're looking at your pen or something, it kind of looks like a circle and a dot. So if you have a vector coming out of the page, you draw it this way. If you have a vector going into the page, you put an X like the back of an arrow, right? Like a bow and arrow kind of thing, okay? So just keep that in mind, just a side note. We're not going to have it for this moment out of the page. For this moment, it's into the page, but keep that in mind. As you can see, this is not like anything mathematical that you've seen before, very likely, right? This is not like addition. This is not like multiplication, like 2 times 10, right? So you likely haven't seen this idea of taking one vector, taking another vector, and getting a third vector that points in a completely different direction. Right? It doesn't point in the direction of R. It doesn't point in the direction of F. It points in a third direction. Okay? So to kind of quantify this, right? So this is how torque works, but you need a mathematical way to describe this. That's why you need a cross product, right? So this idea of torque is defined to be R crossed with F. And it's not multiply, right? So just be careful in your earlier math classes, when you're taking arithmetic algebra, you might put an X to mean 2 times 10, right? This is not that, okay? The X means a cross product. So we'll talk about what a cross product is and how you get these directions that seem kind of strange in a second, but a torque is defined this way, right? So, and R cross F, not the other way around. It's not F cross R. The order of it matters, okay? So it's R crossed with F, right? Gives you the direction of torque. So that's torque. We can't do much with it till we know what a cross product is and spend some time with a cross product. What we're going to do is pause here on the discussion of torque to really understand what this is, right? So this, use a different color here. So this one right here is the cross product, okay? Something you can do with 2 vectors, okay? Okay, so let's kind of hold our discussion of torque so we can actually talk about what a cross product is. So it's a general mathematical idea, right? So you can take any vector and another vector and do a cross product with it, okay? So it's not only related to torque. You can apply it to different ideas, right? It's a general idea. It's like multiplying in arithmetic, right? So 2 times 10, that times the multiplication, that idea can be used for all sorts of numbers, right? It doesn't belong to 2 or 10, right? So the cross product is a general mathematical idea that you can apply to 2 vectors, right? So let's do that. Let's have our Cartesian coordinate system, right? Remember, a vector lives inside of some sort of coordinate system, right? Otherwise, you won't be able to refer to where they point, right? So you want to kind of think of the Cartesian coordinate system as a room, and then the vector lives in the room, right? So you put the vector in the room, and you say, okay, it points in this direction in the room. So let's take 2 vectors, okay? Let's take a vector A that points along the y direction, okay? So call that A. It's some vector, I'm just making it up, right? So some vector is there that points along the y. It's not a unit vector. It doesn't necessarily have to have a length of 1. It's just some vector. And then I can take another vector that, let's say, that happens to point in the z direction. Okay, that's B. Okay, so I have two vectors. Now I want to find what is the cross product, okay? Let's say that's C, okay? C is equal to A crossed with B. Okay? So I want to figure out how the cross product works. So here's where A points, here's where B points, and C points in a certain direction. It's very specific, right? We have a way to figure out where it is, and it turns out we need something called the right-hand rule to figure out which way C points, okay? So there are a couple ways to do the right-hand rule, at least, maybe more, right? It depends on who you ask. And the point is to figure out your way of doing it. Just pick one that makes sense to you. They're both the same. I'm going to show you both ways. They're exactly the same, right? It's just that there are preferences. Some people prefer one, some people prefer the other, okay? So to do the right-hand rule, something that's helpful is this diagram. Let's switch to the slides here, right? So here's the right hand. You want to use your right hand. Don't use your left hand. Make sure you're using your right hand. And one method, as shown in this diagram, is to keep your fingers fixed, right? And not move your fingers around. Your three fingers, right? Your thumb, your index finger, your middle finger, you point it in a certain way, and you keep it pointed in a certain way relative to each other, right? So your fingers stay fixed, okay? So if you can put the camera on my hand here, can you bring up the camera? So this is what I'm doing, right? So I can rotate my hand, right? But notice my fingers are always pointing relative to each other in a certain way, right? I can do this, right? I can rotate like this. I can rotate my hand like this. But notice my fingers are essentially jammed together in a certain way, right? Do you kind of see that, right? So the trick to this is to take your index finger, take your middle finger, take your thumb, and make sure that each of them are 90 degrees to each other, right? And that's the trick. So let me show you. So if I rotate this way, notice my index finger and my middle finger is 90 degrees to each other. And then if I kind of rotate this way, notice my index finger and my thumb is 90 degrees to each other, right? So all three of your fingers should be 90 degrees to each other. That must be the case, right? Otherwise, it's going to not work. So make sure you are pointing those in those directions, right? And yeah, it's kind of like this orientation, right? Does that make sense? Okay, so going back to the diagram, right? That's what the diagram on the left-hand side is showing you. All right, first thing is to put your fingers in those directions. The next thing to do is use your index finger and identify the direction of the first vector. Notice when you do a cross product is something cross something. It matters the order, right? The order matters. So when you have one vector, A, that's the first vector, that's where your index finger should be pointing. Okay, is that clear, right? So notice in the diagram, A points in a certain direction, B points in a certain direction. So you use your index finger and say, I'm going to point it in the same direction as A. Does that make sense? Right. Now, your middle finger, you should go point in the direction of B. Right, wherever B is. Now notice that's what the diagram is showing. Good. And then the result, right, the cross product, C, in the example we're doing, right, the result will be the direction of your thumb. Does that make sense? Okay. So let's switch to the notes again. Okay. It's a different orientation for A and B here in my diagram, right? That's good. So let's see if we can get that, right? So A cross B, you should put your index finger in the direction of A. You should put your middle finger in the direction of B. Your thumb should be pointing at the result. Now, think about it. If you have guesses to where C is pointing, put it in that discussion, right? So that we can see, throw your ideas of where you think is. And while you're doing that, I'm going to show you another way to do the right-hand rule. And if you don't like this fixed finger way of doing it, that's no problem. Let me show you another way to do it. Okay, the other way to do it is to use your four fingers right? Not just your index finger, but your 4 fingers, all of them point in the direction of the first vector, in this case A. Okay? And B is when you take so you start with the first vector and then you want to curl your fingers towards the B direction. Okay, so you start with A, curl your fingers towards the B direction, and once you do the curling, your thumb should point in the direction of what C is, the result is. Okay, so both these methods, the fixed finger way and the curling of the fingers way, both of them will give you the exact same result. There's no difference. It's just that, which one do you prefer? Do you want to do the right hand roll this way? Good. If you want to do the right hand roll this way, good. Pick one, right? It doesn't really matter which one. I prefer one. Maybe I won't say which one I prefer because I don't want to, sway you either way. Do whichever one you want. It doesn't really matter as long as you kind of get the hang of how to kind of put that together, right? Okay. Do we have guesses on a discussion of where C is pointing? Okay. Put some guesses. Right? So is it X, Y, Z? Is it somewhere in between X and Z? Throw your ideas, right? So if you have A and B, your objective is to find where C is pointing. You have to use the right hand rule, right? Because it's not in the direction of A, it's not in the direction of B. That's what it turns out to be, right? It's when you do a cross product, it turns out it's not in either of those directions. It's some other direction. What other direction are you getting?
We're getting X and someone said positive X axis.
X and positive X, okay, good, right? So think about that. Why is that? Let's use both methods to figure this out. I'm gonna probably mess things up maybe I won't zoom out. Maybe that'll mess things up. All right, so let's try to do it with the fixed finger method. And yes, it's a little tricky because you're trying to draw something three-dimensional on 2D paper, okay? So when I draw X, Y, Z like this, I'm trying to do my best to portray something three-dimensional, right? And if an alternative for you is, if I can switch to the computer real quick, is if you go to Desmos, right? You probably use the graphing calculator, maybe a lot of you use it. If you might not know, there's the 3D calculator, right? And what I'd recommend doing is, now with the 3D calculator, you can kind of see things three-dimensionally, right? And you can start, one of their examples is involving vectors, right? So you can throw in vectors, right? So vector V1, for instance, right? It's in, what color do they have it? Orange, maybe? Okay, yeah, this one. Okay, so, oh yeah, there's the orange one. There we go, right? So you can draw a vector in space, right? Notice you can kind of rotate around and see where they point. So I recommend, if you're drawing on paper, it's confusing to you, go on Desmos and make vectors for yourself that point in certain directions. It will do a cross product as well, right? So you can make it do a cross product. As a mathematical operation. So for a vector in Desmos, all you have to do is put vector, and then this is the starting point of the vector, and this is the ending point of the vector, right? If you give those two endpoints, it'll draw the vector for you, right? So just giving the option, if the paper is not working for you, just draw it three-dimensionally, and post on Ed Discussion if you make some cool plots like this, right? And you find, you make a plot of A, B, and label it, and there's a cross product. That'd be kind of cool. So if you can make cool plots, put it on Ed Discussion so everybody else can see it too. All right, switching back to the notes. On paper you can do it too, you just have to use a little bit of imagination that you're depicting something three-dimensional on paper, right? Okay, so A cross B, index finger along A, right? Middle finger along B, and where does my thumb point? My thumb points in the direction of X, okay? So you might want to also kind of do this is the physical model, for instance, right? You can take let's take my pens here, right? So A is the blue one, B is the pink one, and I can kind of put this, right, kind of make a model for myself, right? And if you can bring up the camera, let me try to hold my pens, right? So this is kind of where the vectors seem to be pointing. Let me switch the cap, that way you can see the top better, right? There you are, right? So I have A pointing upward like this, and I have B pointed on your screen going to the left, I think, right? So kind of like that. Is that the orientation you're seeing? Am I doing this? Yeah. We having this way? Either way. So let's say this is the orientation, right? So let's say your vector A points like this. Your vector B points like this. If you use the fixed finger method, right, what I want to do is take my index finger, line it up along A, right, the blue one, and then I have my middle finger pointing along the pink one. And where does my thumb point? Sorry?
Towards us.
Yeah, towards you. Notice it's perpendicular to both of these, right? So if we go back to our nodes, A cross B, the result C is going to point in this direction, perpendicular to both A and B. That's C. Right? So yeah, if the paper doesn't work, if Desmos, right? So you can definitely take 2 sticks, 2 papers, two pencils, right? 2 pens, and then make yourself vector A and B, right? And then have them 90 degrees to each other, and then try to find out where C is, right? So if this is A and B here, right? Where is C? C is perpendicular to A and B, right? And in this direction. So try to use the fixed finger method to figure out where C is. Your thumb should be pointing where C is pointing. Now, just to give you the option, bringing the camera up here again, let's say I have A pointing up like this, B going this way. I can also use my curling finger method, right? And what I do is start 4 fingers along the first vector, and then I curl my fingers towards the second vector, and my thumb points again in the direction of the result, right? So either one works, either one gives you the same result, right? So if I curl my fingers, thumb points this way, that's the direction of C, right? Or I use the fixed finger method, A, B, and that's C, right? Still C is pointing towards you in this case, right? Ask a lot of questions. The cross product can be tricky. Why? Because you very likely haven't seen anything like this before, right? It's going to be odd. So it's important to ask a lot of questions. Make sure, particularly the direction of this vector, you know how to get using the right-hand rule, right? We have questions about it so far?
How do we know that C is pointing along the x-axis?
Yeah, how do you know? Yeah, so that's what you use the right-hand rule for, right? So if we look at our notes and we show this is A, this is B, and this is C, how you know where C is using the right-hand rule, okay? It's the direction where your thumb is pointing. So it's going to take a little bit of practice, right? So I recommend making some sort of model, physical model. Use your pens, use sticks, whatever you have, right? You can use paper, you can use like toothpicks or something, right? It doesn't matter. So make yourself a vector that points in the A direction, a vector that points in B direction. Notice they're 90 degrees to each other, right? And then point your index finger in the direction of A, point your middle finger in the direction of B, and then if you're holding your finger steady, right, remember they have to be 90 degrees to each other. If you're holding your finger steady, you should point your C that is both perpendicular to A and B, okay? Alternatively, you can use the curling finger method, right? So A curl towards B will give you where C is, right? So you know where C is by using this thing called the right-hand rule. Otherwise, you wouldn't know where C is, right?
I'm also kind of confused on like when you point your thumb in a certain direction, like towards you or anything? Like, why is it on the x-axis and not the z or something?
Oh yeah. So let's change this up all entirely, right? So we want a little bit more practice. This is an example, right? This is just one example where I'm pointing A in a certain direction, B in a certain direction, and I'm going to kind of make up another one just so you have practice. Well, let's keep the orientation, the coordinate system the same, because there's no reason to change that, because that'll make it more confusing than it needs to be, right? So we're just going to keep x pointing where x is pointing, and this is y, right? And this is z, right? Now, you can make up vectors, right? So first person shout out, where do you want A to point, right? So let's point A in a direction, either one of these three, right? Yes, we can point A in some random direction like this, but that just makes it harder to see what's going on, right? Use Desmos for that. If you want to kind of make it more complicated and point A in some random direction, you can do that in Desmos, and it's much easier to visualize. But for our purposes, let's just point A somewhere, right? So A already pointed in the Y direction, so let's make up a different direction. Anybody shout out? So we're going to do this live, right? So you tell me, where do you want to point A? 1, X, or Z? We can also go in the negative direction too, right? That's fair game too. So if you want to say negative Z, we can point A in that direction too. So where do you want to point it?
No responses.
It's not a trick question, it's just to pick a random direction, because that way we get something. Otherwise I'll just kind of come up with an example in my head. So I want you to come up with a random direction, so it is quite different from what I would draw. So
The student said negative x direction.
negative x, okay, good. So let's just put A pointing in the negative x direction, right? So here's where A points. Okay, so A points like that. Okay, B, any other direction for B?
Negative y direction.
Negative y, okay, cool. So let's put B in the negative y direction, right? So this is B. Okay, all right, so A cross B is where? Put it in as discussion. Do the right-hand rule, and practice. You don't have to get it right the first time, right? So if you try out the right-hand rule and you guess incorrectly, that's no big deal. We're all learning here, right? So we want to try. The trying and attempting the problem is far more important than getting the correct answer, right? Like, yeah, ideally you want to get the correct answer, but let's try to work on the process, right? You're trying to understand a new rule, right? If I told you this is the word for apple in a new language, you want to practice that, right? If you just kind of look at that word and that it's not going to get internalized, right? You're not going to remember what the word for apple was. So A cross B in this new example, brownie points, if you can put your diagrams on at discussion, if you draw this yourself, if you want to post which way you pointed C, or you can just put in text form, where does C point?
We're getting some positive z's, some negative z's, and
Okay.
then two students said between x and y.
Between X and Y, okay. So positive Z we're getting, negative Z we're getting, between X and Y we're getting, right? So again, three-dimensional thing, this is depicting something that's actually 90 degrees, but if you look at this angle, from your perspective, this might not look to be 90 degrees, right? But I'm actually trying to draw something that is actually 90 degrees to each other, right? So that's why something physical like your pens will be more useful, I think. So if you take A points like that and B points like that, right? So let me try it. This is harder to do when I look at the image and look up. There we go. So let's say A points like this and B points like this, downward. Well, maybe reverse it. Okay, so kind of like in this direction, right? So hopefully you're seeing that, right? So they're 90 degrees to each other, right? They don't have to be, just to, for our purposes, A and B, we're making them 90 degrees to each other, right? So this is kind of how it looks like, right? So when you're doing the right-hand rule, it's better to have a physical model like this because you can rotate and see what it is, right? Otherwise, when you're looking at a diagram, switching to the notes here, it's a little bit harder to see, right? So A cross B, okay, 4 fingers along A, curl towards B. Your thumb should point along the z-axis, right? So let me try to depict this, right, as best as I can. It's harder to do. So with the diagram, so this way, A goes this way, right? And I curl my fingers towards B, right? So B is kind of pointing that way, and my thumb is in the direction of Z, right? So here's where vector C should point. You can do that with your fixed fingers as well. A is the index finger, middle finger is B, and your thumb points in the direction of C. Right, kind of getting it?
We have a question asking if two vectors, when you're taking the cross product, do they have to be perpendicular to each other?
No, that's a good question. So yeah, they don't have to be perpendicular to each other. We're just keeping them perpendicular just to make our lives easier. If you bring the camera up, what you can do is you could have two vectors kind of like this, right? They don't have to be perpendicular. They could be, A could be like this and B could be like this, and you can still do a cross product with them, okay? And this is where the curling method, I was not going to say which one I like better, but I like the curling one a little bit better because it makes it easier to do things that are not necessarily perpendicular, right? So when they're kind of at this, let's say this is A, this is B, you can do A cross B with the curling way and still find out that C points towards you. Much, much easier. So I personally prefer the curling way because I can just have all sorts of orientations, right? So I can have A and B like this, right? So then I go, where's A? My 4 fingers point along A, and then I curl towards B, and then my finger points into the page, right? Back behind the screen here. Right? Are we kind of seeing that, right? So A cross B, finger into the page, right? You do this, right? Which way does it go? A cross B, right? Out of the page. If I flip it over like this, right? Now the blue one is coming, A is coming towards you, right? So 4 fingers, right? Pointing 4 fingers towards you, because that's the direction of A, 4 fingers towards you, and then I curl my fingers towards B, and where does my thumb end up if I do that, right? 4 fingers along A, curling towards B, my thumb ends up downward, right? So this vector C, or the result of this cross product, would be downward. Does that make sense? It takes a little bit of practice, so if you're kind of confused, that's okay. It just takes a little practice, right? So kind of try this out yourself with a little bit of, kind of do some reading, right? Try some example problems, and it will come to you. Ask us questions, right? Practice it yourself. Say, I think A points like this, I think B points like this, and I think C points like this. And when you practice, you kind of get the hang of it a little bit more. It takes a minute, so if you're not getting it right away, that's not an issue, right? Any questions beyond that?
A lot of them were confused about applying the fixed finger method to the second example.
Yeah, go into the notes. This one.
Yeah.
Yeah. So index finger along A, middle finger along B, right? And it's really hard to orient my fingers. So there you go. So that's probably kind of accurate. Right? So here's my index finger going along A. Where's my middle finger, right? It's going along B, and my thumb, right, points along the z-axis, right? It's really hard to kind of show my fingers in this, right? So it's more like that, right? So A, B, and then C is kind of pointing that way. Take this example right? I highly recommend take both of these examples and take some pencils or pens, put some tags on them, right? Put a sticky note or something that one is A, one is B. If you have Play-Doh or some putty or something, stick them onto that, and that way they stay, right? I'm fidgeting with my pens, but if you had like Play-Doh or something, you can stick these into Play-Doh, and that way they stay 90 degrees to each other, right? You might also have do you all have the chemistry sets? Maybe there's a way to get around, maybe you can use the chemistry sets for the molecules. If you have those available, right, if you've taken chemistry or something like that, you might have the molecule sets that you can use for this too, right? So the point is take some directions A and B and then practice the right-hand rule. So with the curly one, the important thing is 4 fingers along the first vector, whatever the first vector is, A, curl towards B, right? And then your C will point. And the trick is to kind of get your fingers to kind of actually do that, right? Because it's not this, right? Because I don't want to put my 4 fingers along A and curl towards B, because it's not really, B is not really in that direction, right? B is kind of sort of coming out of the page because of kind of the orientation of the coordinate system, right? So it's more correct to kind of do it A cross B that way, and then C is also coming slightly out of the page, okay? So it's a little trickier with paper. Try to make a physical model, and then you start seeing the 3-dimensional version, right? So same thing for this. Try both the fixed finger method and the curly method, and then hopefully you figure out, okay, I like one over the other, then stick to that, right? And then that's okay. Okay, so going to our torque, right? So spending a lot of time on cross products because it's important, right? It's a little tricky of a concept. This operation takes one vector and another vector and produces a third vector, right? As you know, vectors have a magnitude, it has units, and it has a direction, right? So the direction part we are trying to figure out using the right-hand rule, right? So this is all an exercise of the right-hand rule, all right? So we're trying to learn the right-hand rule because that tells us the direction of the result, right? So when we have R cross F, the direction of torque is given by this right-hand rule. How do we figure out the magnitude though, right? So we still haven't figured out the magnitude. We need a magnitude, otherwise it's not quite a vector yet, right? So it just has direction, but we need magnitude and direction to make a vector. So what we're going to do is have a rule that says, okay, the magnitude of C, right? And again, C is just arbitrary, just some result of A and A cross B, is the magnitude of A times the magnitude of B. This is just multiplication, like arithmetic, like 2 times 10, right? So magnitude times magnitude, sine of the angle between them. Okay, so here's where you have to be a little careful, because if you have, going back to our torque example, right, with a wrench, notice the direction of R, direction of F, they have a certain angle to them. They're not pointing in the same direction. So when we say this angle, how we're measuring, right, is the direction of A, let's say, is that way, and if the direction of B is also that way, right, we say that the angle is 0. Okay, if they're going the same direction, is 0. If A points like this and B points like this, in the case is somewhat similar to our example with the wrench, then this is an angle of 90 degrees, okay? So the angle we're paying attention to is reference to the first vector, okay? So we're saying if they're pointing in the same direction, then the angle is 0. If they're pointing like this, then we're saying this angle here this angle here is 90 degrees. Okay, and it can be more than 90, right? So it can be a case where A points like this, and then B points like this, right? And what you get is some angle that is larger than 90 degrees, right? And it can go all the way to the extreme of they're actually pointing opposite each other, right? So you can be A pointing like this, and then B pointing, I'm going to draw it right side by side, B is pointing the opposite direction, right? And that we define the angle to be 180 degrees apart. Okay, so just be careful of how you're measuring the angle. 0 is this, they're pointing in the same direction. 90 degrees, right, is that, okay, A points that way, and then B points 90 degrees from the direction of A. Okay, so that you just be careful when you say an angle, you just want to be, that's what we mean. So knowing your sine function, right, so what does sine do? Right, so just remind yourself quickly what sine is, right? So sine, the function looks something like this, right? And it's 0 at 0, it's 0 at 180 degrees, it's 0 again at 360 degrees, right? Either 2 pi or pi, right? And the values it can have, it can go up to 1 or -1, right? So that's the sine function. All right. If you forgot, no worries, just make a plot on Desmos real quick, right? You can see what the sine function looks like. So as the angle changes, the sine function changes, right? If the angle is 0, then the cross product will be 0. Okay? If the angle is 180 degrees, the cross product is again 0. Okay? The cross product is its largest value when it's 90 degrees. Okay? When it's 90 degrees, right, that's when the sine has achieved its highest value here, right? At 90 degrees, it's 1, right? And that's when it's going to have the largest number. Okay? So this, you know, practically speaking, this to be the case, right? Because if you're talking about a wrench, right, you're trying to change a flat tire in your car or something like that, right? You know the best way to hold the wrench is like this, right? You wouldn't put the wrench like this and start tugging on it this way, right? You wouldn't pull the wrench that way. It wouldn't work, right? From your own experience, you know, well, I want to kind of pull it 90 degrees to its kind of arm, right? Same thing with the door, right? Imagine this is not a wrench, but this is a door, right? And you're trying to open the door. You go up to the door, you grab the handle, and then you pull towards you, right? You don't pull sideways, you don't pull at some strange angle, right? You know from experience that if you have a door and you pull perpendicular to the door, that's when it produces the most torque, right? So we're trying to depict reality, right? So all the math is there to depict reality, not just because there's math, right? It's trying to be helpful, right? It's trying to show you that depending on the angle you're considering, then the magnitude of torque, or sorry, the cross product in general, changes as a result, right? So if we apply this specifically to torque, right? So we know the definition of torque is R crossed with F, right? That is the actual full result. The direction of the torque we get with the right-hand rule, but the magnitude of torque, well actually let me write it over here so get some more space. So magnitude of torque is equal to the magnitude of your distance, right, to the force itself, the magnitude of the force, and then sine of the angle between them, right? So in your wrench example, right, if you have a wrench at home, you can see what is the length of the wrench, what is the force you're applying, right? Assuming that you're applying it at 90 degrees, you can figure out how much torque are you applying, right? How are we doing? Questions? Okay. Let's, now since we have the definition of torque, now we can start to think about Newton's laws for rotation. Okay. So let's think about the conditions for equilibrium. Maybe there's a situation where you don't want something to accelerate, right? So maybe you're walking and then you come to a stop and you're standing still. You don't want to be accelerating, right? What's the condition for you not to tip over and fall, right? So it's something that maybe you don't think about as you walk and stop, right? You kind of do it sort of naturally. But there are certain conditions that's true, that's why you're not just tipping over and falling. And that's why sometimes maybe when you do trip over and fall, you don't have equilibrium, right? You are accelerating and rotating and falling, right? So when we had a case of a book, right, that was on a table, well, for the condition for equilibrium, right, starting from the big idea, right, the big idea was the sum of the forces must equal the change, right, the derivative of momentum, right? That's the big idea, Newton's second law, right? From this we said, okay, the mass of the book is not changing, so then we can simplify this to the sum of the forces is equal to mass times acceleration, right? And we said, okay, for equilibrium, we don't want acceleration, and that gives us one of the conditions that we've been using, right? We've used this condition before where the sum of the forces is equal to 0. That's one condition, right? And if this is true, the book will not accelerate in a linear sense, okay? It will not go up, it will not go sideways, right? It won't fall, it will not accelerate. If there are no forces, there's no net, so the sum of the forces is 0, right? Now, there's another condition that applies, right, for an object like a book, right? So here's the book. Because if you look at the center of the book, and I have the case where there's one force like this, F1, and another force like this at the edge, F2, according to the original Newton's laws, right, the Newton's second law, F equals ma, for the constant mass case, this force and this force, if they're equal in magnitude, should cancel each other and would result in the book not accelerating, right? That's what we said, right? But we know that if you did this, it will start rotating, right? If you took a book, right, take it to deep space, middle of nowhere, right, and you applied a force F2, F1, they're the same, and you did this, this is pushing upward, this is pushing downward, and you know this will start rotating, right? So this condition is not enough to say something's in equilibrium. This is enough to say something doesn't linearly accelerate, but here's a case where the F equals ma gives you 0, right? Because if you sum up the forces in this case, it will say 0. But there's something else going on, right? Yes, it doesn't accelerate in the linear case, but it's still doing something else, right? Which is spinning about itself. So the equivalent to this, right, Newton's second law for rotation, is that the sum of the torques, there could be more than one, right? So this is applying a torque, this is applying a torque, is equal to the change in angular momentum over time. Okay, so L is angular momentum, just like linear momentum, right? We'll talk about angular momentum and how you describe it, but remember, we said linear momentum is mass times velocity, right? So we'll kind of do the same thing for angular momentum later, But there's some property that's like mass and some property that's like linear velocity that applies to the rotational case. But for now, that's not important. Let's just keep that in mind, right? So it just follows a similar pattern, so you don't have to really learn a whole nother set of equations, right? It's different in the sense that this is for the linear case, this is for the rotation case, but there's a pattern, right? So that's the nice thing about it. There's something that's like force on the left-hand side, and something that's like linear momentum on the right-hand side. And it also has a derivative. It changes with time, right? So the condition here for equilibrium in the rotational case is that the sum of the torque must equal 0. Okay? So when we say something is in static equilibrium, what we're really saying is the sum of the forces is 0, and we say sum of the torques is 0. If one of these is not true, then something will be accelerating in some fashion, right? So if this condition is not true, then it'll be linearly accelerating, like A. If this condition is not true, then it will be rotating and accelerating at that. Okay, so if you don't want something to accelerate in a linear way and you don't want it to accelerate in a rotational way, both of these conditions must be true. So when we have an object like a light fixture, you're hanging from the ceiling, it's not sufficient to just satisfy one of these conditions. You must satisfy both of these conditions, because if not, it might actually accelerate in the other way, right? If you put a ladder against a wall and you're trying to climb the ladder, right? For the ladder to not accelerate, both of these conditions must be true, right? If it's not, then the ladder will accelerate in some fashion, okay? All right, so let's take a look at this demo that's going to show you kind of the differences here of static equilibrium when you talk about forces versus when you're talking about torque. So once we come back after the demo, we'll look at the math behind it a little bit more. So in this demo, we're going to talk about torque. So torque is R cross F, right? So if you think about this hinge point here, this stick, this meter stick can balance around this point. So let's say if we're talking about this weight, it's 200 grams that we hang this mass, it has a certain weight, and that is a force of gravity pulling down. So there's a moment arm, so there's some radius from the place where the stick is trying to rotate to the weight. So that's your R. So you can use your right hand, use the right hand rule to figure out where the torque is. So you go R, put your fingers along R, you curl towards the force of gravity, the force down in this case, and then you'll see a torque that's pointing towards you. So that's your right hand, right? So R cross F, that's your torque. So there's a torque pointing towards you, and as you can see that if I let go, that's going to cause the meter stick to rotate. Torque will lead to angular acceleration. That's Newton's second law for rotation. So to balance that, we'll use the same amount of weight. We'll put it on this side, right? So now you'll see the two torques are applied, and then they balance each other. So we'll do the right-hand rule on this. So you have an R this way from the point of rotation to the weight, R cross F. The force is downward, so you go R cross F, and your thumb points towards me now. So the two torques are pointing in opposite directions, and therefore they balance each other out. So you might look at this and say, well, no big deal, they're the same weight, so they kind of expect that. But you can do this with a different weight. So let's take something that's a mass of 100 grams. And you can produce the same amount of torque that this was producing so long as you have a longer R. So here I'm going to go further away, twice as far away. So half the mass, or half the force now, and because of that I'm going to move twice as far away. And now again, R, right? So this is your R from this point to this point, that's your R. Cross, downward, that's the force and then you still have a torque pointing towards you. And you can see that if I let go, that is imbalance. That's because still the torque produced by this mass is counteracting the torque produced by this mass, and then they're in balance. So this is a demo of how you can have torque and have that imbalance even if you have different masses involved. Okay, so let's look at that demo. Let's take let's draw a diagram here. Let's say that's the hinge point, the point that meter stick is rotating around. And I can say, okay, there's a certain distance, R1, to the first weight, right? So notice that I can now do things symbolically using variables. What's the advantage of that? Well, R1 can be anything, right? It can be 2 centimeters, 20 centimeters. The weight can be anything, right? So we were trying to slowly get away from specific numbers, right? Because we were trying to understand a general idea. And it's good to work with variables this way, right? It keeps it general. That way you can switch things up as needed, right? So R2 till the weight 2, right? So the direction of where the weight's acting. And always remember, we have some coordinate system to consider when we're talking about vectors. Which way is the vector pointing, right? What's positive, what's negative? And what I'm going to say is I'm just going to use the standard XY coordinate system, right? Now, notice, maybe something you hadn't noticed before, right? Your coordinate system itself is following the right-hand rule, right? So if you have X pointing like this and Y pointing like this in your math class, you probably didn't think about it. You put positive Z coming out towards you, right? Why? Right? Why didn't you point positive Z going down into the page? You could have, right? The only rule that you have to follow is that X and Y have to be 90 degrees to each other, and Z has to be 90 degrees to Y and X. This Z, right, the one that points at you, and the Z that points into the page, both are 90 degrees to X and Y, right? So somewhere along the way, somebody had to decide which way positive Z is pointing, right? And the choice was made, I think, because most people are right-handed, to make the coordinate system itself right-handed, right? So if you do the right-hand rule on your coordinate system, X cross Y, your thumb will point in the direction of positive Z, right? So we are using, maybe you didn't realize this, right? So all this time you're doing math, you're using a right-handed coordinate system. There is such a thing as a left-handed coordinate system. Look it up. And it exists. Right? We don't use it most of the time, right? So most of the time we use a right-handed coordinate system. So that's why we have the right-hand rule, because surprise, surprise, we set it up that way, right? It is subjective, right? So go back in history, somebody could have decided it was left-handed, and we would have a left-hand rule, right? It doesn't really change the physical reality. It's just a choice that we had to make. Somewhere along the way, we made the choice that it should be right-handed, okay? So I think it's probably because most people are right-handed. So that's why. So XY, the positive Z comes out towards you, right? So I'm going to draw a circle and a dot to depict that's the direction of Z, right? All right, so now we are going to sum the torques, right? For there to be static equilibrium, what we want is the torque, right? One of the conditions for this is that the torque should sum to 0, right? So let's sum up all the torque. Well, let's go over here, right? The nice thing is that these two are 90 degrees to each other, right? So when we're actually doing this calculation, when we know that they're 90 degrees to each other, sine of 90 degrees is 1, and that makes it easier to work with. All that is just a simple multiplication, right? You still have to worry about the sign, though, right? You pay attention to the sign, because you need the direction of torque, right? That determines SI-GN sign, right? So we need the magnitudes, right? So all we do is R1 times the magnitude of the weight. That's this. We do the right-hand rule, right? So 4 fingers along the direction of R, curl the directions towards the direction of the second component of the cross product, which is the weight, and then your thumb is pointing towards you, right? So towards you is positive, that's a positive direction of z, so then we leave that as positive. Do the same thing for the second part. We know the magnitude, okay, r times the weight, okay, those are the magnitudes, right? We're following our cross product rules, right? So the cross product is magnitude, magnitude, sine theta. Sine theta is just 1 in this case, right? Is it positive or negative, right? Okay, we use the 4 fingers going towards R2, curl, right, towards the weight 2. Thumb is pointing into the page, right? So go R2, curl, R2 is that way, curl down towards W2, thumb is into the page. That's negative z, so this is a negative number, right? So that has to equal 0. That's our condition for equilibrium, right? So that's why you can move the weights around, you can put different weights, so long as this sums to 0, then it's not going to rotate, right? You can set it in such a way and sure that's not going to rotate because it cannot accelerate without any net torque on it. Doing okay? Like I said, a little practice is necessary. It is a little tricky. It's not just you, it's everybody, including me. When you first learn torque, it is going to be strange because you've never seen such a thing before, right? You have a vector that points in one direction, you have another vector that points in another direction, and the result of doing something to those two vectors is a third vector that points in neither of those directions, right? So it takes a little bit of getting used to. So just do some practice, do the reading in the textbook, right, just to get you a little bit more familiar, more problems, right, and we'll go from there. Okay, so a couple of things to talk about before we end class 1 is the center of mass, okay, because it's an important concept, because if we're going to do an Insta-poll later, when we try to calculate static equilibrium conditions, you have to kind of figure out where to put the force of gravity, and we need to sometimes figure out where that force acts, and it's through the center of mass. Okay, so let's say we have our XY coordinate system, and we have a bunch of particles scattered around. So if you wanted a real world scenario, think about playing billiards or pool, right? And on the table, scattered around a bunch of balls, right? And each one, let's say, has a certain mass. We'll keep it general so that all the balls don't have to have the same mass, right? They're different masses. They could possibly be the different masses. But the question here is, what is the center of the mass, right? So all the masses kind of scattered around. Where is the center? So if you kind of look at where all of them are, you might say, well, it's probably somewhere there. You probably guess, right? And so what we're saying is, okay, we're trying to find out that location of the center of mass, right? So if you have a bunch of particles like billiard balls or pool balls scattered around, notice that the center of the mass could be nowhere near an actual mass, right? It's just a location in space. If you have an actual object, like a pen, then of course the center of mass of the pen would be somewhere inside the pen, right? Okay. So how do we calculate the center of mass? First, what we need to do is sum up all the mass, right? So big M is we're going to do a sum, right? Greek symbol sigma. J is the index. Start with 1. So each particle, 1, 2, 3, 4, right? It has a number. Go up to all the number of particles. If there's 10, that's 10, right? So count all of them. One by one, go find its mass, add them, right? It looks scarier than it actually is, but all it's saying is add all the masses, right? take each mass, mj, right? J is the index, m1, m2, m3, m4, right? All the way through all the m's and add them all up, right? You get the total mass this way, right? It looks scarier than it actually is, but it's just saying do a sum, right? All right, so once you do that, you need that because the center of mass is 1 over the total mass and another sum, J is equal to 1 to all the particles, where you go and take each mass and multiply it by the distance from some location, in this case our 0, 0 point, right? You need a coordinate system. This is kind of a theme of the class, right? You need to establish a coordinate system because if you're going to measure a distance, you're going to measure a velocity with respect to what is always the question, right? So some of these things are subjective. Position is subjective. Your water bottles at a certain position relative to what? The corner of the room, Mars, right? Like, where do you mean? So you have to establish a coordinate system. So when you're measuring distances to each particle, you have to say, where are you measuring from, okay? Looks kind of mathematical, of course, right? So let's try to do an example. As you'll see, it's not too bad. Okay, so let's do an example where you have 3 particles, right? So here's one that's 4 kilograms, one that's 5 kilograms, one that is 2 kilograms. Okay, and we'll pick the origin to measure distances through the middle one. There's no reason for that. It's just I'm just picking the middle. You can pick this one, you can pick this one. It doesn't matter, okay? Okay, so the distances, each one is 3 meters apart. Okay, and we want to find where is the center of mass, right? Now, even before you do anything, look at this is 2, this is 4, this is 5, right? Take a guess of where the center of mass is. Just like we kind of did here, you can kind of see this has 4, this has 5, this is 2, so where should the center of mass kind of be biased towards? To the left, up, to the right? Yeah, it's biased towards the right, because there's clearly more mass on the right-hand side than the left-hand side. So when we get a result, hey, does that fit what we expect, right? So we want to kind of make a guess, right? Always make a guess, like, hey, because otherwise you get an answer, you might say, oh, that's the answer. But if you get an answer that says, oh, it's right next to the 2 kilograms, well, something's probably off, right? All right, so we're calculating the location of the center of mass, which is equal to, well, first thing we want to do is the total mass, 1 over the total mass. In this case, that's 11, right? So 1 over 11 kilograms. Then we have to multiply, right? So 1 over m multiplied by all of this. All of this is a sum, right? Mass times the distance. So we start with one particle and just carry on. So we have 2 kilograms. So we have 2 kilograms. Its position relative to our center point, minus 3 meters, right? Because we're measuring from the 4 kilograms. The 2 kilogram is minus 3 away, right? Our coordinate system is such that it kind of follows like this, right? So x and y. We don't really need y in this case because everything is along the x-axis. So minus 3. And then we say 4 kilograms. How far is it from the measuring position? 0. Right? We're measuring from 4, so that should be 0. And then we do 5 kilograms, and then how far is it from 4? 3 meters. Okay? So as you can see, it's not too bad. It looks like this, but really in practice what you're doing is take 1 over the total mass, take each of the masses and how far they are, multiply them together, and do that over and over again to all the particles. And when you do that, you get something like 0.81 meters. Right? And that's measured from the 4 kilograms in the positive direction, right? If the center of mass actually was in the opposite direction, in the left-hand side, then it would come out negative, right? So when you're putting in these positions, right? So just be careful that you have to put the signs. They're not absolute values, right? You want the actual position relative to the place you're measuring from. You can extend this to 2 dimensions. Right? So this is just in the x direction in this case because that's all we need to care about, right? But if you say, well, what if it's like our billiard ball example where you have 2 dimensions to think about? How do I find the center of mass of that? Well, you do the same thing just twice. Okay, so let's say instead of all the particles being lined up like this, it was more of a situation like this, right? Where you had, let's say, the 2 kilogram right there, and then the 4 kilogram was over there, and then the 5 kilogram was over here, right? Now, same scenario. What you want to do is establish a place to measure from. So let's say you want to stick to the 4 kilogram, and you say, okay, that's my x and y. Okay, you're measuring distances from x and y, and believe it or not, you're still applying this rule. Only thing is, you've probably seen the pattern. When you write a vector equation like this, it's deceptive because it's actually 3 equations hiding in there, right? So whenever you're writing a vector equation, just be careful. That's not just a single equation. So to find the center of mass of this scenario, what you have to do is center of mass in the x direction, right? You do the 1 over the 11 kilograms, and then you do the same thing where you go 2 kilograms times the distance of the 2 kilograms in the x direction only, right? So yes, the 2 kilogram is now somewhere over here, but what is this direction, right? What is this distance? That's what you're putting in here, right? So some negative x value, right? And then you add the 4 kilograms. Well, that's where the coordinate system is, so that's 0 again, 0 meters. And then you add the 5 kilograms, and you say, okay, where is this located? Well, it's located there, and it's got a positive x distance. Okay, so that's some positive x value, right? Put that in there. And then you get this result. This result is the x component of the center of mass. Now you want the y component, you do the same thing, 1 over 11 kilograms. 2 kilograms, again, right, same thing. Where is the 2 kilograms relative to the origin? Well, it's got a negative y value. Put that negative y value in, right? And you get the idea. 4 kilograms, again, it's at the origin. Add the 5 kilograms. It's got negative y, right? So negative y component, add that, right? And then you do this, you get a result, and that's the y component of the center of mass, right? So you can still follow this, right? This kind of recipe you can still follow in 2 dimensions and also 3 dimensions, right? It's the same thing you're doing over and over again, right? Okay, so why the center of mass, right? So center of mass is important because we're going to switch to our computer because we're going to do an Insta poll on a meter stick. A little bit different than the demo, but give it some thought here. Always draw a picture. Okay, to start with. Let's take about 1.5 minutes, whatever you work on it. Draw a picture, put all the forces, right? Make sure you have a coordinate system set up somewhere, right? You're measuring distances relative to some point. Start thinking about equilibrium. Some of the forces, some of the torques, right? That's what you need to be thinking about. And what we're trying to solve for, right, is the mass of the meter stick. We want to figure that out. So let's take 1.5 minutes, have you work on it, post questions on Ed discussion, and we'll be back in a bit. Okay, so hopefully you've got a chance to work on this a little bit. I'm going to switch over to the notes, and I'll put down what's in the problem as we go, right? So you want to always start with the picture. So we have a meter stick. Okay, and start labeling them. So you know the distance is 1 meter or 100 centimeters. And they say there's a fulcrum, and it's kind of a balance point, right? So it's, imagine kind of it's balancing at a certain point like this. That's what they mean. And that distance is 25 centimeters. Okay. So it's supported at that 25 centimeter mark. There is an object, right, that is hung from the zero end. Okay, good. So let's put that. So there's some object here, right? And we know that is 0.5 kilograms, and then we can multiply by g to get this force, right? So this force, call it 0, right? How do we get that? It's the weight of the object, right? So 0.5 kilograms times g will give us that force, right? Just kind of dipping it down. And the stick is balanced horizontally, okay? And it's asking for the mass of the meter stick, right? So now we're looking at the forces applied, right? And there is this connection point that it's about to rotate. It can rotate about that point. And the force that's missing, right, you want to ignore it, is the weight of the meter stick, right? So the force due to the weight of the meter stick, we can say, is the mass of this meter stick times g, right? Now, why did I put the weight going through the middle like here, right? I know this is 50 centimeters, and how do I know that? Is because the center of mass of the meter stick is at the halfway point, right? Because if I go ahead and use my idea of how to calculate the center of mass, and I kind of split up the meter stick into little pieces, and I calculate how far they are, it'll end up that the center of mass is right in the middle. How do you find? You can also find that out by taking an object and trying to balance it, right? It balances at its center of mass. Okay? So when you have an object and you're thinking about gravity, the net result of it is that the force seems to act at the center of mass. Now, of course, gravity is pulling on this part of the meter stick and this part of the meter stick and this part of the, right? The Earth is pulling on all parts. However, the net result is as if it was centered at the center of mass by a certain amount, which is its weight. Okay? All right, so we want to sum the torque. Right, so sum the torque, and that's equal to 0, right? And so I want you to try this out, right? See if you can do this. We're going to sum the torque, and we will pause here because we're kind of coming towards the end of the class. We'll pause here, we'll pick this up, but think about how you would figure out what the torques are. About which point would you calculate the torque? Right? These are some things you want to think about. So don't worry about the Instapoll for answering that. That won't be a problem. We'll just carry it forward to the next class, right? So just a reminder, tomorrow is a holiday, right? So no class, of course. We'll pick up on Friday with continuing with this problem, carry on. Quickly looking at the syllabus real quick, looking ahead. Just pay attention to what's coming up. There's 2 homeworks that have been posted already, 3 and 4. All the homework leading up to midterm 2 is now available, right? So that's all the material that's going to be covered by midterm 2. There are different due dates, right? The next one, homework-wise, is due, I set it to be, I think, Tuesday, right? Yes, right. So Tuesday of next week, because Friday we have a holiday, it's shorter week this week. So Tuesday, then the following Friday, right? Back to our homework schedule as usual. Tomorrow, Juneteenth, right? So holiday, we'll come back. We'll have a full week of class, and then the following week we'll have midterm 2, right? So, and then we have another holiday coming up, right? So fast pace, of course, it's the summer, right? Just keep up with your reading. Don't forget your reading, right? The reading assignments are already on the syllabus, right? So make sure you're keeping up with the reading. Make sure you're doing your homework regularly, right? So don't just put it off and 3 days later try to answer the questions. Start them right away, right? Keep working on them every day. That will help you with the material. Don't forget, come talk to us during drop-in hours. We're happy to help, and we'll see you after the holiday on Friday.